morning, ladies and gentlemen. My name is Alexey Belosirkovsky. I'm kindly inviting you to the second day of the 15th International Conference on Pattern Recognition and Information Processing. Yesterday we had a great day with plenary speakers and as well as session speakers. So we also had an informal meeting in the framework of a virtual drink cafe. We call it virtual drink party. So we had informal chat with people from USA, Canada, Russia, Ukraine, and as well as Belarus. So it was nice. And I hope that all speakers today already in charge now, at least those who are, will present the papers and the results in the first session. So now, nothing else to add. I'd like to invite you to the first plenary session, and let the science begin.
Artificial intelligence. We objectively assess the importance of this topic. However, there is still no consensus on whether all tasks can be solved using these technologies. Abuse or obligatory use, we will raise such issues of ethics, modern information society, and cybernetics. This is the story of our virtual conference on pattern recognition and information processing in 2021, which has already begun. Here, right now.
We're coming back to our studio, and I would like to present you our chairman of the first plenary session, Professor Vasily Kovalov, Dr. Vasily Kovalov. So you have a floor now.
Okay, thank you very much for your kind introduction myself. Now we have a plenary session with invited speakers, with two professors, and I think it would be very successful because they hold really extensive experience in the field we are working in. So first, by Professor Henning Müller. Henning Müller from Switzerland, and he studied medical informatics at the University of Heidelberg, Germany, which is a very famous place in all the respect. Nearly every one of us visit that one day. And then after that, he was worked at Daimler-Benz Research in Portland in the United States. And from 1998 to 2002, he worked on his PhD degree at the University of Geneva in Switzerland. And then he developed his career further. And what I want to also to say that from 2002, 2002, actually he moved to the field which is close to my own research, which is medical image analysis and such kind of thing. During that time, also he visited Harvard Medical School in Boston, which is a very well-known place for that kind of research and development. And he's now in Sierra with the university, which is difficult to pronounce for me. But anyway, you can read it because on our site you can read that text. And he's also recently heading large European projects. And what is specifically important for us, for me, that he also visited Minsk several times, and I hope he get a little bit patriotic about Belarus and PRIP conference. And also we have some sort of collaboration. In particular, we are running together the challenge international competition, which is called Image Clear. And also, by this reason and some other, we visited that place several times. What I would say specifically interesting for me, it was our visit to Lugano, to the conference about that competition, Image Clear. Switzerland is an interesting country in the respect that in order to get from one city to another one in Switzerland, you need first to get to Italy, to Milano. So we travel from Sierra to Milano and then from Milano to Lugano. back to Switzerland. And the funny point was that all the tickets we had for train were not valid. They expired 2 days, but that was really an adventure story, and it was very interesting. I will be remembered it all the time. So let's back to the matter. And Henning will be giving a presentation which is called the ExaMode project for large-scale multimodal data analysis for decision support in histopathology. So many people move to histopathology nowadays. That's very interesting. Okay, thank you, Henning. That floor is yours right now.
All of this, so I don't talk much about it. But what I wanted to say is that I've really been working for over 30 years now in between hospitals and computer science, so really looking at building applications and collaborating with clinical partners that we have. And as you mentioned, universities may be difficult to pronounce, but and we're really in the middle of like southern Switzerland. So most people know Zurich, Geneva, and this is Milan actually, where you change trains when we went to Locarno. And we're sort of right in between this triangle. And usually I show them up because people don't know we're serious, because it's quite a small city. But most people know the Matterhorn, so that's really close. So that's about out here, so maybe 30 kilometers from where we are here. And this is an aerial view just to show you a little bit the environment. So it's quite a nice place to be. But in terms of the topics, so I wanted to talk about the ExaMode project, which is an acronym for Extreme Scale Analytics via Multimodal Ontology, Discovery and Enhancement. So we can see here already a couple of the keywords that I mentioned in the title as well. So multimodal, combining text with images, looking at ontologies, also semantics, and really improving everything on a very large scale. Histopathology, you mentioned, Vasily, that many people are now working in histopathology because it's starting to become digital and available at a larger scale. So whole slide image scanners have been used for, I think, at least 15 years, but it's been only in a research setting. Now, really, many histopathology departments actually integrated into the clinical workflow and really scan very large numbers of biopsies. That said, the images are about 100,000 by 100,000 pixels. So it's pretty large. And usually we don't only have one, but several of these images per patient. And it's funded by Horizon 2020, so the EU framework program. It's quite a selective call, and we receive about €5 million with the 7 partners. And what I wanted to show is we have a regional split of the partners in the project, and also a split in terms of the topics. So I saw that there's also a presentation, I think, by Sara, so the Dutch Supercomputing Center. So they are making their high-performance computing infrastructure available for us, because we really want to make sure that we can go at a very large scale and that we could treat everything that a very large histopathology department in a university hospital would be treating. Then we have 2 academic partners, University of Padova and us. So Padova are working on semantics and text, and we work more on the imaging side. We have 2 medical partners, the hospital in Catania, which has been fully digital for the clinical workflow for a while, and also Radboud University Medical Center, which is also one of the pioneers in digital pathology and image treatment. So they provide images, annotation, but also test the tools and try to integrate them into the clinical workflow. And then we have 2 industrial partners, OntoText from Bulgaria and Microscope IT from Poland. And the objective is that they pick up the tools that we develop and they bring them to the market. They integrate what we do. So we also have a sustainability plan with respect to what we do in a project. Just to give you a little bit of an idea about, I checked out the amounts of data that are being produced. And I'd mentioned images that are 100,000 by 100,000 pixels. So we easily have 10 gigabytes per image. And they are now digitizing millions of glass slides and perfume-embedded blocks. I made a quick calculation. So if we have these 86.5 million images times, I mean, if we have 100,000 by 100,000 pixels by 3 bytes per pixel, we're at like 2,600 exabytes of storage. I mean, I don't know how they will exactly do that, but I'm pretty sure they need to find a couple of interesting solutions, but really look at very large scale analysis in this respect. And to show you a bit of an example, so these are needle biopsies of the prostate. So this is maybe 1 millimeter or 2. So they are really, really fine needles that are stuck into your prostate. And for one patient, you might usually get like 12, 15 of these biopsies. You can put 2 or 3 on a single slide. Then you can zoom in. You can zoom in further. And then you're at the microscopic level. So pixel size about 250 nanometers in that case. Compressed images are about 10 gigabytes in size. There's a very large variability due to the process that is linked to so we have samples. So this can be rat, mouse, human tissue. It's embedded in a block of paraffin. Usually it's sectioned, then put into very thin slices, and then it's colored. And particularly the coloring process is currently what adds a lot of variability into these images, because every lab has their own way of doing it. But even the sectioning depends on the temperature, so it's really, really thinly sliced. But if the sample gets warm, the slices get thicker and they might be compressed. So all of that adds to the variability. But then it's mainly the stainings of chemicals that highlight specific parts in the image, such as nuclei and connective tissue, for example. And currently, most of the image acquisition is analog. So pathologist looks at it at a microscope. But with digital pathology, these slides that are stained are now scanned. And when they are scanned, we can actually do quantitative analysis. So we don't only have like the qualitative analysis here, but we can go to the next report and also do semi-automatic report writing. So this is something that we would like to do in this project. So really getting into this clinical digital workflow that is now installed in many hospitals. This doesn't mean that all of the images necessarily need to be stored long-term. Quite often, storage is only like a subset is stored in interesting cases, etc., because the tissue samples are actually kept in a tissue bank, because like that additional cuts could be done, or genetic analysis if this is something needed. Deep learning has really shown very good results in several applications. I mean, not only on images, but particularly on images, and also particularly on histopathology and several scientific challenges, results that equal histopathologists that have been shown, because there's usually a lot of disagreement actually among experts when they annotate images, when they mark images. So using decision support can also help to harmonize that and limit this disparity and limit the subjectiveness of some of these applications. But as I said, images are large, so we need much computation. The regions of interest, so that determine staging or grading of cancer, are often very, very small. So we really need to look into small areas of the images. What we usually do in like extracting patches all around the images, or doing a multi-scale analysis, because different anomalies are seen at different scales. So histopathologists will start look at the global images and then zoom into specific areas where there are small changes that might be important with the highest grade of a cancer, for example. And we need to, if we want to use deep learning, we need to really think about the heterogeneity, because we want to make sure that what we do generalizes to all of the images that are produced in clinical routine, so even under different conditions. And that's why it's important to have a fairly large heterogeneity in the training images as well, so it really corresponds to what we need. As I mentioned, what we would need for deep learning is usually very large amounts of data. I mean, that's difficult because of ethics, privacy constraints, medical data are more difficult to obtain quite often than other data. But particularly here, the images are large, and using complete annotations, it is prohibitively expensive. So we putting a pathologist down to mark very many image regions is something that experts are rare, and they're very expensive. And we need expert knowledge to really do the annotation in high quality. Another challenge we often have, in many medical fields, is that machine learning works very well with balanced data sets. So if all of the classes are reasonably represented. If some of the classes are very rare, this often creates a disadvantage for these classes in terms of the classification. Unfortunately, or fortunately for many people, there are many cases that are rare, actually, particularly in screening. You have very few positive cases. So we actually need to look into how to train these algorithms so we can limit the false negatives, because we really don't want to miss out any of these. It's the same thing for high-grade cancer, so it's pretty rare. But again, we need to make sure that particularly these cases, we actually get them. So we need to have a good representation of rare cases, abnormal cases that do not frequently occur in clinical routines. And then we really want to have a large variability in terms of staining, but also in terms of scanners, machines. And there are new machines that we produce that are introduced into clinical routine. We need to make sure that all of that really is represented in the training data. So what we want to do in ExaMode, or what we're currently working on, and we have quite a few results already, is to limit strong labels, so annotated regions. We want to have a few annotated regions, but much of it we want to work with what we call weak labels, because we do have reports for basically all of the images in the image archives. So we have a description of the image that a pathologist wrote at the time when the image was used for diagnosis or treatment planning. So we want to leverage this data to have weak labels, but then very large amounts of data that allow us to still learn important things. And for that, we combine semantic knowledge from the reports with the image data that we work on for multimodal analysis. And we started actually developing domain ontologies for the fields that we attack in our project, and then use the weak labels, make it scalable. And another part that we wanted to include in terms of the data to be used is also using images from the biomedical literature. There's PubMed Central that actually makes text, images, PDFs of open access literature available. It's the National Library of Medicine maintaining this, and there are millions of images that are available, and we do have a bit of a clinical context. But among these million images, there are only a few images that are actually relevant. So within the project in ExaMode, we decided to use 4 use cases, so colon cancer, lung cancer, and cervix uterus cancer, mainly due to the fact that these are all areas where screening programs exist, where there's a large number of biopsies, and it's labor intensive. So somebody reading the images takes a long time. And that, as a result, has a high economic value, where also the companies that are part of the project could really profit from. And then the last one is celiac disease. So basically a gluten allergy, where because we wanted to have one non-oncologic application, and it is strongly increasing in numbers. So there's also a very large number of biopsies that are available for this. And as I said, based on the reports that were extracted from our hospital partners, we started really looking at all of the entities that occur in the reports and all of the entities that are linked to the specific types of cancer that we're treating. So for every one of the 4 use cases, we really modeled the domain with ontologies that can then help us to map free text also in different languages. We have reports in Italian and Dutch, and then we have the literature in English. So we're in a language-independent domain pretty much. And we also developed a viewer annotation tool for these really large images, because we have to zoom in, zoom out. So having a very efficient tool to manually annotate regions, to validate regions, to show overlays, what you can see here. So we can segment specific parts, we can show them. A user can manually annotate parts and add labels, all of that. So that's called Virtum. It's from Microsoft IT, so one of the company partners. And as I said, we have 2 clinical centers that supply us with data for the 4 use cases. And then we try to also use openly accessible data sets. So actually with scientific challenges, Vasily mentioned the tuberculosis task that we've been running. There are many other challenges that use histopathology data, such as chameleon challenges. There's TCJ, the Cancer Genome Atlas, and TCIA, the Cancer Imaging Archive, that also have hundreds of data sets that are made available, that are shared, and that we try to leverage. Also to really check all of these aspects of generalizability. So we train with one data set, test on another one to see whether we actually just capture the main principles of a specific data set, or whether we're actually becoming data set independent, and shows that if we use a large number of data sets for training, then it generalizes much better to unseen data sets as well. And we use the open access literature, as I said, PubMed Central. I think there are over 5 million images. Many of them are compound figures. So they consist of several subfigures. There's over 20, 30 million images that are made available. But again, much of it is noise. So it really requires a massive cleaning to become possibly useful. And also on that, we have organized, I think, 6 or 7 years now of image clay challenges where we've worked on the data, manually annotated them using crowdsourcing. So we have many different techniques that are available. The big advantage of the literature is, there's a large variability of images, so much variety in terms of staining, many different labs, many different scanners. Also, if there are new machines, new scanners that come up, quite often this is what people actually would publish on because they have a new type of image. So we would automatically get this into our training data as well. And same thing, really unusual, rare cases are used for publication. So this is something that we can then also use. We oversample actually these rare, unusual cases. And as all of these images have been obtained with ethics approval, we can actually use them freely. So most of them have Creative Commons licenses attached that allow us a non-commercial reuse for scientific purposes. Yeah. So it's there are many rare images, unusual, untypical. There might be a few typical cases, but usually it's the extreme cases that are shown. And this allows us to get a critical mass for rare diseases. Many laboratories increase generalizability, and it's an exponentially increasing content. So we can actually retrain regularly, and like that, we would really adapt what we can do. And if you're interested, there's more information on how to make this available in this article here, where we analyze a little bit also what we get out of these cases that we detected for histopathology. I mean, these are just a few steps that we needed. I gave a few images here. So these were initially classified by our algorithm as histopathology. I mean, this is not at all histopathology, but you can see why our algorithm mistakes it. And that's also why we need to retrain, manually check, adapt it. This is actually a hand-drawn histopathology image. So the class was actually hand-drawn image, not histopathology. But I mean, I think you get what the algorithms get and why we really need to look at some of the fine differences. We then classify all of the images that we have, like the 5 million images, into figure types. We actually also detect compound figures or multi-pane figures that we can then cut apart and reclassify the single figures. Remove everything that is non-relevant. So here we want to focus on histopathology. And for histopathology, we then need to check for human and animal tissue. Fortunately, actually, PubMed Central has manually attached labels. So there are the National Library of Medicine, there are human annotators who actually attach labels such as human, animal tissue. It doesn't exist for all of the images. I think 90% of the images have such labels attached. And for the remaining ones, we can then check for similarity actually with human versus animal. And that actually leads to very good results as well. And then we figure out specific organs, so the organs that we're interested in. And then we can look at what are the diseases, grading, staging that we would like to have. And like that, we can actually, I mean, in the end, we end up with a small number of images, but these are then very interesting images from the standpoint of heterogeneity. I mean, this is just an example of compound figures, but we can actually automatically detect these data and then cut them apart and then check which part of the caption actually corresponds to them. So we also get ground truths. But again, this is multimodal data analysis, so checking text and images. And actually, natural language processing in medicine is far from trivial. I gave a couple of examples, like abbreviations. You can see here, AB has actually 15 different abbreviations. And so you really need to look at the context you're in, and then you can try to understand it. But it's important to have these dictionaries. I mean, this is from Wikipedia, so there are dictionaries of medical abbreviation. There's also spelling mistakes in reports. It's quite common because quite often they're quickly written. Sometimes technical language, Latinized terms, also synonyms. So here, heart attack, I mean, you can say heart attack, cardiac arrest, asystole, cardiac infarction, cardiopulmonary arrest. I mean, I think there are 25 different ways of saying the same thing. And obviously, we want to look at concepts. And so we put everything together. Then there's often nested complex phrases and a lot of negation. That's actually the main part in the written reports that we have, because they want to include or exclude, confirm or exclude specific things. But then we have many things in between. What does it mean, little evidence of? It doesn't mean no. It doesn't mean that it's not present, but it's not 100% sure. So we actually need to look at like all of these levels and then check in these nested complex phrases what it corresponds to. Sometimes we have double negation. So it's not easy. And then combining this with the images is actually where it starts really interesting. One of the things we realized when we used the images was that we actually lose all of the metadata. So when we have the histopathology images that come from a scanner, we know what is the size of a single pixel, but in the literature, all of that gets lost. I mean, they might talk about magnification, but actually the editor might modify the images, like upsample them, downsample them when they're put into print. So what we wanted to do is really look at like, can we detect automatically what is the magnification of these images? So we looked at images from the literature. We also generated from whole slide images different magnifications, and then checked how well a system was doing. And we had a brute force deep learning system. And we had one where we segmented nuclei and we were looking at the nuclei size, but enlarged nuclei actually linked to specific diseases as well. So if we only take the nuclei size, we might actually create other problems or errors, because we might then use incorrect information if one of these diseases that causes enlarged nuclei exists. But in general, the results are pretty good, and there are data sets for benchmarking that were made available, so we compared also to the best results in the literature, and actually we had better results than what was published before. And then, as I said, we looked at some data sets where we have strong labels. So this is the data sets with tissue microarrays. This is actually for prostate. So it's something that we did in the beginning of the project to test the tools while we were annotating data ourselves. And this is from TCGA, where we have global labels. So it's Gleason scoring, Gleason labels that we were using that we then tried to predict. And we checked, do the fully supervised using weakly supervised learning, and then doing combinations of the two, each time also testing on the other data sets to see how well we can predict it. And what we can see is actually that the results get, I mean, not bad. We use kappa score, so it's agreement between two raters. So we check what is the reported agreement between two human raters, and then how well do we get. And what we can see, the more training data we get, actually the better the results get. What we see is also that actually the results continue to increase. So likely adding even more data than we currently have would further increase results and would actually bring us very close to human raters. Another approach that we used was to use a teacher-student model. So we used strongly annotated data to create a teacher model that we then use on the unlabeled data. And we need to find a threshold where we believe that the results are actually of sufficient quality. And then we pseudo-label these patches. So these are not manually labeled patches, but automatically labeled patches. And we use these then to train the student model. And in the very end, we then use the strongly annotated data to fine-tune the student model. And that also shows us, I mean, there's a publication here that it actually really increases results and leads to very good outcomes. As I'd seen in the program that there's also, like the next speaker talks about interpretability, I also just wanted to say that interpretability is actually one of the things that we identified at the beginning of the project to be a major factor for acceptance of clinicians. So if they want to use the tools, we cannot just use a deep learning model as a black box, but we need to be able to explain how we came to specific decisions. And one of the things we looked at is what's called concept activation vectors. So it's from computer vision. It's been team of Google Brain who developed this approach, where she looked at, like, for example, for a zebra. So what is the concept of a zebra, and how do these then look into how we can classify how zebra-ness a specific image is like. So we looked into implementing this similar approach for medical images, and we actually called it regression concept vectors, because in the medical field, often we don't have like specific binary classes, but we actually do have like more of a regression thing. So for example, enlarged nuclei, as what is shown here, I mean, you can have very large nuclei, you can have small nuclei, or slightly enlarged nuclei. So it's actually a regression problem that we wanted to have. And what we can then check is how these points such as nuclei size, internal heterogeneity, border heterogeneity, so this would be texture, this would be heterogeneity of the borders, how this actually is related to a specific decision. So this is totally independent from the network, so we can use any network, so we're not altering the quality of a network, so we can really use deep learning with its good results, but try to explain by annotating a small subset of the data and checking what are the activations inside the network. We can see which part of the decisions we can actually explain with the characteristics that we're having here. I mean, it has advantages and inconvenience, because here, I mean, the nice thing about deep learning is you don't need to manage features. And here we create sort of features that we use to explain something. But what we often do is that we actually work with clinicians on what they currently use. We try to model that computationally and then map the decisions. So we can see, are these actually the features that are most relevant, or is part of this decision maybe not explained? So we can also look at hypotheses. They feel like, but there's something else that might be of interest, and then we can check that out. So this is ongoing research work, and it's actually quite interesting to see. We can also check to remove specific parts of the networks to optimize outcomes by using domain knowledge, which can also help us to make things better explainable, but also really increase quality and limit some of the biases that can occur. But for example, if we want to, I mean, here we don't want to be scale invariant, because size actually is an important factor. I mean, there's many such things that play a role in medical images. And currently, we work on a white paper on AI-based decision support and how we can integrate this into the pathology workflow. What are the factors that we influence? So we've done a couple of surveys. So if anybody knows pathologists who are interested, don't hesitate, I can send the survey. But also, what is actually affected by AI-based decision support? So do we increase speed, efficiency, or effectiveness, or quality of a decision? Maybe also the trust that people have in the decision, and maybe even helping semi-automatically with the report writing. These are the kind of things that we're currently looking for, but it's not yet finished. And so I was told that I have a maximum of 30 minutes. So I think I'm reaching the end slowly. So what I wanted to talk about in this is really the ExaMode project on histopathology image analysis using deep learning tools, multimodal data analysis. And I believe that there's a lot of potential. I mean, it's a very active domain with really much research going on. Manual annotating images is expensive because we need physicians. They're often overloaded, so it's very hard to actually get access to them. So even if we have funding for them available, we really want to use that in the most efficient way possible. We really want to make sure that they only work on tasks where we actually have an information gain. So we don't want to annotate things that don't add anything to the classifier. That's also why we really want to work with global labels in as much as possible, and checking how we can leverage text reports that generate global labels to then identify patterns that are linked to the global labels. And if we have enough data, this is something that's absolutely possible. But it requires strong computing infrastructures, GPU computing, CPU computing. That's why we need our national data center to help us with this. And I do believe that also in terms of security of the data for medical data, it's good to have these secure infrastructures. And if you need more information, I think the European Commission for their funding on examode.eu, you can find more information on the project, the outcomes, the deliverables. And then we also have the web pages of our group, or you can contact myself. And I mean, so we're here on Zoom. You can see the last meeting a year and a half ago was at Sara in Amsterdam. So that was the last physical meetings. And since then, we've basically had Zoom meetings every time. So it's also making it difficult for the project because I think with brainstorming, etc., it's actually much more effective than Zoom meetings. And thank you very much for your attention. And I'm now open for questions or comments, feedback, and anything.
Okay, thank you very much, Henning, for your nice presentation. And please, questions. You can write them in YouTube, I suppose. You can voice them using your microphone, please.
We have none.
Okay.
There's one question.
Sorry?
Yes. So can I ask here in this?
Yes, of course.
Sure. Please go ahead.
Yeah. Okay. So thanks, Henning, for this very inspiring talk and about this exciting work. So what is very interesting is that because you're outside the formal clinical settings with this large repository. So do you have some experience, like from how many different sources do you need data when the models start generalizing? So after you have maybe from 3 or 5 clinical centers, it doesn't matter whether you have number 6, 7, 8, or 9. Do you see like some kind of saturation of variance that you need in your data?
I mean, in principle, it depends on the variability of the centers. So we have the Chameleon data set, which is publicly available. And I think there are 5 or 6 centers, and one of them has actually very different images from the others. So when you use the 5 centers that are similar, not the 6th one, actually the results are not very good. It doesn't generalize well. Whereas if you include this center and you remove any other center, the results are fairly good. So I think what is important is to cover with the existing training data the new centers that are tested, so that it's not an outlier. Other than that, I mean, if the centers are reasonably similar, usually after 3, 4 centers, the results get pretty good. But still, if you have something that is really different, it still creates problem and doesn't generalize very well. So it's good to actually check beforehand, like some of the maybe technical measures of the center. So what's the color spaces? How do the images in general look? Some quantitative measures to see whether there's a risk that this is actually an outlier before doing tests. And I think that's also something when you buy a new machine, for example, it's good to check and actually at least produce some data to validate that it generalizes to these data.
So in your data, when you get really very broad sampling of data, can you also infer, because probably you not always have the information, like from which device do these data come from? Can you sometimes even speculate or classify from what kind of device these data were generated?
Actually, we haven't done this for histopathology, but for radiology, where we use a data set of phantoms. And it's trivial to identify the producer. So to specify between Siemens, Philips, GE, and Toshiba is absolutely trivial for computed tomography. And even detecting the machine is pretty simple because the texture is really different. The algorithms vary there are differences for the same machines between hospitals. So it's not always installed in the same way. And it also depends on the clinical protocols. But we just also finished a study where we actually 3D printed a lung and liver phantom and scanned it in all university hospitals in Switzerland and a couple of private clinics as well to see like what is the variability of that. But machines make a big difference, and this is something that, we need to take into account when we develop algorithms, that we don't have these systematic bias. There's a pretty big risk of bias.
Yeah, thanks.
Thank you. More questions, please? Maybe I got one. So anyway, I want to just confirm that this multi-central studies is very problematic due to differences in scanning, in preparation and scanning of samples, and also in radiology. All the devices have some specific signature. We even provide experimentation when we just recognize the device, and it's works pretty well. So anyway,
it's actually interesting because you can remove that. So we use the generative adversarial networks to actually check what is specific for a machine and what is non-specific for a machine. So we use that on the phantom data set, and then we could actually create images that do not have these, so that do not allow this classification. But then the risk is that, these were purely technical analysis. So we would need to check with radiologists actually how they see the images. So it's something that we haven't done on the clinical data, but it's something that we plan to do on the 3D printed phantom, where we actually use clinical data to print the phantom. And we hope that there we will get a bit more of an idea of like how much it affects the results, because obviously we don't want decisions to be depending on specific machines or parameters of the machines.
Oh. Okay. What I want to add also that this deep learning and convolutional neural network, they are very, very deep. They have millions and millions of trainable parameters. So at the beginning of our work in this 5 years ago, we tried to, and taking part in different international challenges. We just run different training for different sources. For instance, norm on pathology. And then we realized it's not necessarily actually to do this way. Because of the capacity, of very high capacity of neural networks, you just put all together. And if they are well annotated, then the results are reasonably good. So the process when we want a hematoxylin iazine images to make similar, very similar, because they are coming from different hospitals and they look different. You immediately see that some of them very dark, some of them like pine. Well, okay, anyway, we put all together and it works at the end of the day. So,
yeah, I mean, we also did some systematic analysis. So if you're interested, I can also point you to some of the papers where we compared data augmentation versus image normalization versus a combination of the two. And I mean, the two obviously model similar information. I mean, data augmentation often works pretty well. On the other hand, it is also not necessarily the most efficient approach, not the most elegant approach, because you need to have arbitrary parameters that you use for that. But we also made available at some GitHub a tool for normalizing H&E stained images. So if you're interested in that, don't hesitate. I can send you the links to this.
Thank you. So my own question, actually, the last one, I suppose, is this about the generation of artificial images. So we provide certain experimentation that there is some functionality in our website for generation of histology images, and we provide quantitative assessment of the artificial images versus real images. So, can you comment, please, on that? Do you think it worth to consider the problem of generation of artificial images or case of histology?
I think it has advantages and inconveniences. I mean, the advantage of generating images that can then be used is that you don't have the ethics constraints in general. I mean, that depends on how they are generated, because if they are generated based on real images, you really need to check like what are actually the licenses for the real images, because quite often, at least our ethics committees don't necessarily allow us to like train models with images and use them to generate something else. But indeed, I mean, it's a good occasion to add variability What is the risk, on the other hand, is that it gives us the impression that we're having actually something that should generalize, because we generate images with different parameters. But on the other hand, I mean, real images might have different variabilities, so it might not actually help us that much to generalize. But that depends on whether the models we use to generate the images actually corresponds to the changes in real images that might occur.
Okay, thank you very much. So, thank you once more. And now we are moving to another presentation, which will be done by Professor Axel Mosig. And because we are out of schedule a little bit due to technical delays at the beginning, so I would put complicated things simple. So, Axel is from Bochum, Ruhr University of Bochum, and he is heading all the bioinformatics, let's put in that simple way, all the bioinformatics things in that university. And we are lucky to have him today, and we are lucky to say we're in collaboration already, and that's building you see now on the top. It's pretty nice building, a brand new one. Perhaps, no, okay, Axel not able to see through his window the Mont Blanc, but it's also, there are some greens around, and that's pretty nice and pretty good building, and with a lot of capacities, including different kinds of microscopes. That's just very rich in that domain. And the supercomputers, all that stuff on the basic floor and underground. So that's pretty good condition, and they doing pretty good, interesting research. And it was my pleasure previous week to take part in this nice seminar which we have together. Okay, Axel, please go ahead.
So Axel, please unmute yourself. Now you're mute. Yeah.
Okay. No. Okay. Yeah. Thanks, Vasily, for the very nice introduction. So I'm just like Henning, I would be much happier to be able to visit Minsk at this moment. I remember the very nice workshop almost exactly 2 years ago, or a bit more than 2 years ago, which I enjoyed very much. And I would enjoy much more being in Minsk than sitting in my home office at this moment. I'm also glad that I can stand on the shoulders of Henning's talk, who already introduced quite a bit about computational pathology. So I can go through these parts quite quickly, and I think you will see that we have from also the experimental work that we are building on, we have quite a particular perspective on the field. And that also shapes our computational approaches. So first, a brief map about myself. So I started with my undergraduate and PhD studies in Bonn. Then I was a postdoc. I had the enjoyable 2 years as a postdoc in Leipzig in Peter Stadler's group, which took me even further to the east, to Shanghai, where I was a founding member of a Max Planck Partner Institute, and I stayed there indeed for 6 years. And so after going to China as a German computer scientist, I sort of came back as a Chinese biologist. I came back to Germany because I was then hired by the biology department in Bochum in 2011, where I have been now for more than 11 years, sitting door to door with experimentalists, which I think has really shaped our work and our way of thinking. And I hope I can get this across also in my talk. So a bit about the history of computational pathology. So like so many things in the digital world, computational pathology happened as a collision between two fields that were out of that were unimaginably out of touch for decades and centuries. So pathology started with the Greeks and also has its roots in the Arabic world. Modern pathology was shaped by Virchow. So these H&E stains that you have seen in Henning's talk, this protocol very much dates back to Virchow in the late 19th century, end of the 19th century. And since then, actually, pathology did not come up with really major innovations until computation came around with, of course, the steep development of machine learning, artificial intelligence, and the resulting impact on computer vision. So I don't need to give you much examples about computational pathology after the talk by Henning. Here is just one example from our work. So we have these gigapixel images of whole slides which easily reach hundreds of thousands of pixels in each dimension, and we want to identify disease-associated areas, for example, localized tumor or localized evidence for certain tumor subtypes. Experimentally, this has also been already introduced in Henning's talk. So histopathology mostly relies on this H&E staining. So staining samples by hematoxylin and eosin, where you see the nuclei in purple and the cytoplasm in pink. So you can localize the nuclei. If you look at the samples under the microscope, which of course nowadays with digital slide scanners and so on can be done quite well automated, despite of course all the heterogeneity due to the experimental procedures involved. In Bochum, we are utilizing one very particular approach to microscopy that deviates from kind of the mainstream in computational pathology, yet leads to also very interesting computational problems that we as the bioinformaticians in Bochum are working on. So we utilize infrared microscopy. What is infrared microscopy? So here in the background, you see like a last generation infrared microscope. So what infrared microscopy gives us are hyperspectral images at a resolution that is not quite as high as the conventional optical microscopy underlying that you get from the slide scanners. So we have a pixel resolution of about 5 microns, which is roughly a factor of 10 away from a factor of 10 less than the optical H&E staining. But we do get a spectral fingerprint at each pixel. So we have hyperspectral images, and this infrared spectrum is highly characteristic of the biochemical status of the sample. So at the cost of slightly lower resolution, we get really molecular, highly localized molecular information. That is a bit difficult to interpret what molecular changes do we really see, but that's part of the computational analysis that drives our work. And our approach then is that really interpretable and explainable AI is really at the core of our work, because these hyperspectral images we cannot visually look at these hyperspectral images. So we inevitably rely on computation analysis and computational interpretation, which we always aim to combine with molecular evidence of what we see. So this is the philosophy of our work, and that roughly follows this workflow that combines computation and experimentation. So we have the infrared microscopic image. We somehow want to really segment and localize the disease-associated areas. Then there is a technique called laser capture microdissection, where one can really cut out specific areas from the sample and analyze them with other bioanalytical tools. We can, for instance, use omics technologies, genomics, transcriptomics, proteomics to analyze, also lipidomics could be, to analyze what we see in these disease-associated areas, and that will give us the molecular interpretation that where we want to be able to use infrared microscopy to see things at the molecular level that are not identifiable at the visual level, for example, in the conventional H&E staining. Before I really get to describe the deep learning methodology that we developed for this in the second part of my talk, in the first part, I want to give a brief or an excursion into the interplay between inductive machine learning and the deductive reasoning that is behind experimental research. So machine learning, that is what we always have to keep in mind, and we see it in these problems of generalization. Machine learning is inductive reasoning inevitably. So when we perform supervised machine learning, we always have, we usually split our training, our data into training set, validation set, an independent test set. In clinical or medical research, independent test set very often needs to be from a multicentric clinical study. And well, what we run into is that in this visualized sense here, so our training set and validation set are maybe very clean and similar. So we only see white swans, and the black swan that affects the performance of our machine learning system negatively is only present in this multicentric validation data set. So in the end, when working with medical data and multicentric data, which are important for practical machine learning systems, we cannot really rely on the assumption of independent and identically distributed test data. So the IID assumption has its limitations in medical analysis, and that's what makes the machine learning for medical data both challenging but also interesting. So the sources of variance, of course, for histopathology are, well, there's a long chain of processing the samples and the data. We can have unseen variances in the patients, in the way samples are being extracted, in the way the samples are being further processed in the microscope and devices. So all these, we have a chain of probably dozens or maybe even hundreds of sources of variance. And some of these in multicentric studies will inevitably lead to these black swan events. So when we now think about machine learning or supervised machine learning, it's, well, in the end, it's not much more than fancy way of interpolating our training data when we train such a network. And so this is affected by this famous quote written here: even after the observation of the frequent conjunction of objects, we have no reason to draw any inference concerning any object beyond those which we have had experience. So this sounds very skeptical of supervised machine learning. But in fact, this quote precedes supervised machine learning by 200 years. It is due to David Hume, describing the problem of induction, which translates to machine learning. And in fact, the translation of the problem of induction to machine learning is the accomplishment of David Wolpert with the no-free lunch theorem, basically proving that machine learning inevitably has inevitable limitations of generalization power. So there are inherent limitations of inductive inference. In practice, of course, in medicine, we always keep looking for seeing more and more variance until we see that the models generalize, which works in practice in many cases, but there always is the danger of unseen variance. One way to address this problem, of course, we have also seen this in Henning's talk, is explainable machine learning. So the idea is to really learn based on domain knowledge, teach our models to maybe learn based on domain knowledge, learn concepts. When we look at swans, we may learn about swans having a long curved neck and a beak and feathers, and an interpretable machine learning model may tell us, okay, in this image, I see all the features of the swans that I have seen so far, except it is black in color rather than white. So this is how explainable machine learning or concept learning could give remedy to the problem of induction. And this, of course, leads us to our approach of molecular interpretations, where we have seen, so we, on the one hand, we have the inductive inference of supervised learning, but then we change the domain of experimental research, where, well, it is well known that experimental research is hypothesis driven and follows deductive reasoning. And in fact, we are not the first ones to really think about molecular interpretation, but there is a nice quote by Rudolf Virchow, the father of modern pathology. Cellular pathology is not an end if one cannot see any alteration in the cell. Chemistry brings a clarification of living processes nearer than does anatomy. Each anatomical change must have been preceded by a chemical one. So this captures very well what we consider the basis for molecular interpretation. However, there still is somehow this dichotomy between inductive inference of supervised machine learning and the deductive approach of experimental research. And this, well, we can have a closer look at. First of all, what does it mean if we train a machine learning model? What does it mean to make this model interpretable? Mathematically, it is just a very simple extension. Namely, we extend the output by an addition. We do not just reproduce the trained class label, but we give an additional output from a domain that is somehow interpretable, an intermediate induced domain that tells us something about the internal workings of the machine learning model. So then we get two outputs. But the question is, how does this translate to deductive reasoning? So in machine learning, we always go from specific observations to a general model. This is the inductive approach. In deductive reasoning, we have general hypotheses and apply them to specific samples. This is deductive reasoning. So these somehow go in different directions. And one can, so if we have such interpretable machine learning models, we can indeed combine these two worlds by phrasing a hypothesis that, following Popper, should be a falsifiable one. So we can now formally define an interpretation of a machine learning model as a falsifiable hypothesis that connects the inferred output of a machine learning model with a sample that the input data originate from. And there are many important details about this definition. It's first of all important, and that distinguishes this definition from previous definitions. So many definitions always go back to the data. Going back to the data in experimental research is very limited, because one cannot conduct any further experiment. This is only possible if we go back to the sample, where now one can derive a prediction about a secondary type of experiment. And it's also important that the hypothesis relates to this interpretable state of the model, because the label is something that is already very well defined. So if we phrase a hypothesis that relates to just the well-known class label, that doesn't help. But here the hypothesis basically phrases a conjecture whether the machine learning model has really learned something meaningful, and relates it back to the sample where this conjecture becomes testable. And so this definition is, in that sense, it unites the worlds of inductive machine learning and deductive experimental research. which of course so far is just theory and thinking about it. Does it really? So does this really matter for machine learning methods? But for us, and this takes me to the second part of my talk. So this really has shaped shapes the way we think about developing deep learning methodology. So what has in the past 2 years has sort of become our working horse for infrared microscopy-based computational pathology is this comparative segmentation network. What we always need, in particular when we think about laser microdissection, we always need pixel-precise segmentations. So all the convolutional neural networks, ResNets, AlexNet, GoogleNet, VGGNet, these don't help us so much because we really want to get to the pixel level. So we really need segmenting networks, and we have already seen in Henning's talk, these require quite substantial efforts of annotation, which we cannot really afford, and which is in fact difficult for infrared microscopy. So what we do is we collect patches of suitable for such a segmenting unit as an input, and we collect samples. We collect such patches that we have one set where, for example, we are very sure that this contains a certain minimum amount of cancer, say at least 10% cancer. And then we collect an equal number of cancer-free samples. And then the CompSegNet infers the differences and infers a localization of the differences between these two classes. So that immediately leads to the hypothesis that the activation that we get out of the UNet actually corresponds to tumor. And it also sets it apart from other approaches to interpretable learning, namely that this hypothesis, we already use this hypothesis during training. So we really use it to control the inductive bias. In other words, we use the hypothesis and the inductive bias of the network as a modeling tool. And this is kind of the way of thinking that we have developed out of working with infrared microscopy, which I think is also relevant or potentially relevant in other applications. So how does this CompSegNet work? The idea behind it is actually fairly simple. So we want to train this UNet without actually having a segmentation. So we turn this segmenting network back into a classifier by simply pooling the activations at the output layer. And then we train on, well, this pooling neuron having high activation for the cancer samples and zero activation for the cancer-free samples. This defines a loss function, and one can, with a little bit of caveats about transfer function and treating background, one can actually train classifying networks out of segmenting networks out of it. This works fairly well. So here is a comparison for some samples where we annotated the overlay of the infrared image, which was the H&E stained image. So here in purple, we see what was annotated as tumor by the expert. Blue is other tissue than tumor. Black is background, and green is what our network, what our CompSegNet has identified as tumor. And we can see it really co-localizes reasonably well with die scores ranging between 0.5 and 0.6. And also we can perform ROC curves on larger sets of samples that really tell us that also when there is no cancer, we have really very little to no false positive activation. Of course, we are also interested, how does this compare to post-hoc approaches? So the probably most famous post-hoc model interpretation approach is linear relevance propagation, which trains a CNN, and then after training the CNN without this inductive localization bias that we use for the CompSegNet, it performs backward propagation, which areas in the input domain were the main contributors for the classification outcome. So this can also be applied, of course, to histopathology images. This is now a study not based on infrared microscopy, but on HE staining. And here we see LRP also localizes the tumor very well. So we have the same color scheme for both samples, ComSegNet on the left, LRP on the right. The dice scores of the ComSegNet are slightly higher. And one difference that also lies in the methodology is that LRP has a tendency to over-detection and the ComSegNet has a tendency to under-detection. Okay, now we can localize disease-associated areas reasonably well. And now I want to talk about one computational challenge that arises from using laser microdissection. So it first of all sounds fairly simple. You have this device, you just transfer the coordinates of your segmentation to this laser capture microdissection, which is just a simple geometric transformation. And now the challenge is the device then can cut along this border and gives a laser pulse to shoot out the sample. However, this has certain problems. If the fragment that you cut out is too big, it simply will not fly. If it's too small, it will be burned. And if it is not convex, it will break apart. So there are quite strong constraints, feasibility constraints that these fragments need to satisfy. So here is one example how this really looks like in practice. Here is one tissue sample on the left-hand side, seen in the H&E stained version that you can perform after infrared microscopy. You can do a semantic segmentation. So here we want to dissect the green class, that is the class that we are interested in. So we get a binary mask. We can do we can clean it up a little bit with some morphological transformations. And then the foreground background mask falls apart into connected components. And here is one of these connected components. So this one is way too big. Again, it would not be dissolvable from the microscopy slide. So we have to subdivide it into smaller parts, as is shown here on the right-hand side. And what is also shown here is our main computational tool to perform this subdivision, this polygon decomposition, which is the morphological skeleton of the sample. So how do we perform this polygon decomposition? Here is an artificial shape that illustrates how we do it. So we work, of course, we sample along the skeleton, and we look at certain root points in the skeleton. So the skeleton, if we don't have holes, it is simply a tree. And so we always, if we have an internal vertex in the skeleton I, then P of I is like the skeleton at, if we take I as the root of a subtree. And now we have we can mathematically prove certain properties, namely that if P of I, it could be that P of I is already feasible. It satisfies all the constraints, and we can dissect it right away. However, if P of I is not feasible, then we can prove a relatively simple decomposition property that there exists a smaller polygon also rooted at I, such that this polygon P prime is feasible, and then the remaining polygon P of I subtracting P prime also possesses a feasible decomposition. Okay, so this is illustrated here. It can be, this polygon P prime can be very simple. just a short stretch, and then we can decompose the gray shaded area. It could also stretch across branching nodes. That's what makes the problem indeed computationally difficult. And then we kind of have to follow several subregions. So this property can be translated into an efficient dynamic programming algorithm, and that indeed gives very smooth and stable decompositions of even very fragmented shapes that we encounter in our samples. The different constraints. So this is a very generic concept. We can combine it with several optimization criteria, like minimizing the number of components, having size constraints, having fatness constraints, minimizing the cut length or maximizing the fatness. So this really facilitates a whole lot of different constraints that yields us the tissue composition that finally allows us to perform these molecular validations. We have also validated how big is the tissue loss if we perform, if we follow this approach, and we find that the tissue loss on average is somewhere around less than 15%, and that is significantly more than applying like a naive decomposition method that just somehow performs bisection, which loses more than 30% of the sample. Okay, finally, in the last, but I will only go through this very quickly. So we also now increasingly work with H&E imagery. We do some work in cytopathology, for example, where we get cellular samples from urine sediment, and we want to figure out, does the patient suffer from bladder cancer, which can be detected by spotting cancerous urothelial cells in this ocean of, well, 10,000s of cells that we see in such a whole slide image. The problem is we only have sample labels. It's very difficult to annotate these cells systematically. So really want to train end to end. And for this, to just go through this very briefly, we have developed, or we have adopted the state of the art of multiple instance learning, which considers whole slide images as bags of items. Each item is a cell or a CNN patch. And the assumption is that in the positive bags, there's only a small number of positive instances, whereas in the negative instances, there are 0 positive instances. So this matches very well cancer detection. Also, multiple instance learning has had major impact in computational pathology just very recently. And we figure with certain adaptations of attention mechanisms and so-called hard negative mining, we indeed get very strong results in cytopathology. So using just a relatively small cohort of 20 versus 20 patients, so not a multicentric study, I have to say, we significantly increase the performance that we get from also quite recent reference methods, which achieve accuracies of slightly below 90%, and with the so-called gated and attention combined with hard negative mining, we get up to 96% accuracy. So as take-home messages, I hope I could carry our point of falsifiable explanations that connect inductive machine learning with deductive experimental research. It leads to the idea that inductive bias is not something, is not a hardwired property of machine learning models, but it is actually a modeling tool that one can use to set up problem-specific machine learning tools that lead to interpretable machine learning. I think we are just at the beginning of really following this in a systematic manner. And also laser microdissection. This, I think, is maybe something that probably has a big future in the context of pathology. I think we have spotted a computational problem that one needs to decompose these shapes to fully exploit the method. This, I think, will also have has quite some potential of impact. With that, I first of all thank all my students and group members and collaborators, both in the mathematics department and sitting door to door with us in the labs in the research building that we are sitting at, all the sponsors, and finally I thank you for your attention, and I'm glad to take your questions.
Okay, thank you very much, Axel, for your nice presentation. It's very broad, it's very nice, and it is very inspiring as well. Like I said previous time last week on our seminar, the last presentation was really inspiring for me. Okay, thank you very much. Now we have time for questions, please.
Vasily, I would like to ask a question.
Yes, please.
Yeah, thank you very much for your excellent presentation. I would like to make one comment concerning your results on skeletons based on boundary representation, because many publications were devoted to skeletons, but as far as I know, and I've seen the book of people from Moscow State University who published very interesting results on the fast computation on skeletons based on boundary representation. It is just what you were using, and maybe for you it will be useful to know about their publications, because they even published a book devoted to this subject. Mm-hmm.
Okay. Yes, I'm very interested, and indeed, I mean, we collaborate. So our collaborators here are really computational geometers in the math department in Bochum. So we are very interested also in the theoretical foundations, and indeed what we need to do. So the skeleton in the pure mathematical definition, it is a highly branched structure. So it has a lot of small but not very relevant branches. So we rely on having pruned skeletons. Of course, there is a very clean mathematical definition of the medial axis of a polygon, but we always rely on simplifying this. And indeed, in terms of this simplification, there has been some recent progress on pruning skeletons, but we are very interested in also in other fields or in
okay, I will find this book and I will send it, because it's another approach which was developed, as far as I remember, people from France on fast computation of skeletons based on boundary representation, not on morphological definitions of morphological skeletons. But I would like to stress that on boundary representation is very important, and it was devoted even to fast algorithms, how to get a good skeleton without these false skeleton lines, which usually are removed by pruning of the skeleton. So I will send to you this information.
This sounds very relevant for us, so I would be very grateful.
Thank you.
Thank you very much. Please, more questions. Okay, anyway, you can write them down and they will be considered. Let me ask two short questions, hopefully short. One is a stupid one. Do I understand correctly for multispectral images, the first layer of filters is just something like 3 by 3 by n, where n is number of channels in spectra? Is this correct?
Okay, so where do I have, so here the input layer to our models is, well, the hyperspectral. So we assume we have the tile size of 256 times 256. And then in this example, so the spectrum, each spectrum has 427 wave numbers. So it's a three-dimensional matrix of dimensionality 256 times 256 times 427. After that, what we do in the next layer of the network, we just use, also for some practical reasons of not making our models excessively large, we just use the standard UNet architecture. What is indeed a critical thing that is happening here, and we are also looking for ways to improving this. So usually when you work on RGB images, you have a feature expansion, because here this dimensionality of 128, sort of like the spectral depth of representation, 128 is much bigger than 3 in the case of RGB images. For our hyperspectral images, the opposite is happening. So we are reducing from a feature depth of 427 to a feature depth of 128. So in fact, here is something like a dimensionality reduction happening, the opposite. In practice, the models work fairly well, but we also are experimenting with dimensionality reduction techniques, using autoencoders and UMAP representations and principal component analysis to reduce the input dimensionally, combining this. So this is definitely a point where I would say we have not fully understood everything that is going on.
Thank you. And maybe a last comment on the problem of labeling of images, multispectral images because it's clear that that's the problem. It's even labeling is difficult by itself, but then it's multidimensionality coming into the game, and then it's becoming even more complicated. So what we notice, for instance, from that Challenges International, even ordinary hematoxylin iazine, 30% in the Panda challenge, 30% of labeling was wrong. Simply done by biological students, and it was done wrong in Sweden. So what kind of problems and solutions could be considered here in the context of multispectral images?
Okay, so, well, of course, first of all, practically what one can do and what is often done, one can, because the infrared imaging is label free. After the H&E, after the infrared imaging, one can just perform the conventional H&E staining, register the images using, for example, STAS approach, and then annotate the H&E image. This is, of course, where we want to get beyond this. So, and then one has like the same problems and limitations as for annotating H&E images with a lack of experts. And so that is, in fact, somehow the idea behind our molecular interpretation approach. So our idea is to infer segmentations just on the basis of data, and then use molecular characterization to see what segmentation can be inferred, which, of course, the idea is to overcome the limitations of what one can see in H&E images. And so that is roughly our approach to, in the long run, of course, we would hope to get rid of visual annotations and really rely on molecular assessment.
Thank you very much. That's very advanced things you are doing. Thank you very much. Thank you also participants for participation in this nice section. So I'm really happy that we did it, that kind of session. Thank you very much once more. And now we are going further according to the program.
Yeah, so I would also like to thank you, dear colleagues, that you agreed to participate in our conference, and so we had actually so exciting talks from you. Well, for others, please. Currently, we have a break. You may take a breath, 1 or 2 breaths, or take a coffee for the next session. So it's not too much time, but still, so it is enough for coffee at least. So and the 15 minutes before 12 on CST +1 in Minsk time, we will come back for the next session. I hope all speakers will connect to the session. And for the audience which follow us on YouTube, please subscribe and ask your colleagues to do the same, because we need to get up the channel on the YouTube. So it's very important for us. Thank you again. Thanks to all of you. So we will come back in next 7 minutes, I think. Thank you.